Welcome back to Pop Goes the Stack, where the hype cycle is loud, but sometimes it points at something genuinely transformative. Really, sometimes. I am your host, Lori MacVittie, and we're going to separate the signal from the press release today. Joining me, as sometimes, is our co-host, Joel Moses.
Yeah, sometimes.
You left me alone for so long.
I'm so sorry.
I missed you so much.
I know. App World Grand Tour.
That's right. He was on a world tour. But today we decided we wanted to tackle the all-important question, debate. I don't know. Anyway, you got AI, there's inference, and there's training. And they're the same, but they're different. And they have all sorts of different terms that go with that and different requirements. And we wanted to kind of dive into that because the model's not actually learning at real time. I know it remembers your name because it does, but it's not permanent, right? Once you close the browser, it goes away. Okay, it's only there for a while. So we want to understand the difference between training, which actually teaches it things long term and it remembers, and inference, which is runtime and mostly in memory, and quite frankly, it's inference. So to dive into this, we've got Ken Arora. Welcome, Ken.
Hey, welcome. Thanks for having me back.
Yeah. Well, you're going to argue with Joel, so I'm all for that. I'm ready. And we've also got Kevin Baughman, who runs our AI Center of Excellence. So he knows a thing or two about this subject, which is why we brought him on, to keep us all honest. So welcome, Kevin.
Hey, thanks for having me.
Awesome. All right. So I'm just going to kick this off because, I think that's my job here. So you've got inference, you got training. Like, why does it matter that they're different, and how does that impact, the infrastructure, the compute, the stuff you buy? What do you have to have in place? What does it mean? Why do we need to know?
Yeah. Well, Lori, honestly, I don't necessarily think, at least from a mathematical perspective, that there's a lot of difference between training and inference. There's different amounts of math that you have to do in order to do the training. You have to do a backpropagation check, and that is expensive computationally. But if you look at the actual mathematics behind inferencing and training, they're identical. They're just done in different amounts and with different data sets incorporated. Training isn't about more math. It's about remembering things. And training, inference can discard like intermediate information or results after they're used, but training has to save every intermediate activation because it has to go and backpropagate. It has to go perform a whole series of checks. The metaphor that I like to use is the one about the piano tuner, which is that you can hear someone play a wonderful composition on a piano, but what led up to that piano being in tune was someone had to go and play a bunch of notes on it and then watch to see whether the notes were correct and correct for any flaws. And so the kit that they may have around that is different. The amount of time that they spend on it is different. But we only hear on the inference side the playing. We don't hear the tuning.
I was a physics major. Differences matter. Fundamentally, we're all 6 quarks that are put together in different ways. And my chemist friends will say we're all a bunch of atoms that are just put together in different ways. So, absolutely. At one level, you're absolutely right, Joel, right? It is the same compute infrastructure, but at another level, because it's put together so differently, the differences matter. Yes, you can buy GPUs, and in fact, you could say, okay, the GPUs are the same, but even there, you see a split between hardware and silicon and ASIC data paths that are optimized for one or the other, and that's a whole nother podcast topic. But the high order bit here is that those differences matter. If I try to go into your piano analogy, you're absolutely, you talked about this. Yes, you're playing a piano, and you've got this. I'll make it a digital piano because it might make the analogy a little better. Right? There a lot of work goes into identifying what the sound is on that digital piano and making, people in a test lab somewhere in Yamaha are working on it and speaker placement, all these great things. And that's a huge amount of time and investment. And then they take that piano and they replicate it, make thousands of copies, and ship them off to wherever. And that's shipping that piano is sort of like the model and training the model. They did that in the lab, and then you go off and you play it, and you can play it in many different ways, and that becomes inferencing. And you can play anything from hip hop to classical music on it.
Sure.
Right, and that's wonderful. And that's the inferencing part. Yes, you're right, it's still a piano, but the workflows around it, how you go about doing things, what you take as the input. The input for the composition is going to be somebody playing jazz or somebody looking at sheet music. In one case, in the other case, it's some labs and technician using acoustical equipment to see what a piano sounds like. So it's, in my mind, yes, both are pianos, but they're very different. Let's, Kevin, keep us honest.
Yeah.
No, I 100% agree. The other thing that I keep in mind is when we're building these systems, for a while, we were only thinking in the large language model world about training. Everything was focused on training. And then when it came time to start using these things and deploying them at scale for users, the thought process was very different, right? Versus one big environment versus a bunch of smaller ones. The other thing is how these things are used is training and inference. To me, has gotten blurred very much right now with large language models, is because people are using context to change the behavior. It's almost like you're performing inference on different data, but that data contains rules on what you want the system to do. And it's ephemeral, right? It's a short-term learning, but occasionally we can get these systems into states where we can never reproduce it again. So it's really, how do we think of inference and training? Training to me always has been frozen weights. Inference always has been deterministic behavior, and that's all been flipped around.
But what does that mean? I mean, when you're training, we associate tons of data, like high volume, right? Just big chunks of data. So obviously the security around that coming in is going to be different than protecting, from prompt injections. These are two different processes, correct?
Well,
everybody agrees we're done. That's
to some degree. I mean, Kevin brings up a very interesting distinction, which is that the ever-increasing context window means that you're saving a lot more intermediate state and you're reusing it as part of the inference chain, which is more work. I mean, it involves more work. It's a little closer to doing the math that would be you would do if you were creating a model from scratch. Although the scale there is tremendously different. I mean, your training sets are much, much larger than your intermediate context window sets are.
Where is that stored? Where are we storing context windows? Maybe that's
memory. We're storing it in some memory somewhere, right? So a training set is going to correct, but a training set, if you're doing a training run, you're talking about using up to 40 gigabytes of memory attached to your fast GPU complex in order to just hold in state all the things you're going to need for the gradient. And so that's a lot, but we're not really accepting 40 gigabytes worth of context window information. That would be nutty,
insane,
and and it would drain your bank account fairly quickly.
Yeah. So think about it this way, right? Training bakes things in. It's like baked into the model, baked into the piano you shipped are all these things. The context window is more about a certain level of maybe how I might place the piano in the room to get good acoustics. There's another level of this, which Kevin will probably bring up in a minute, which is fine tuning. And the reason I mentioned the digital piano is, right, the piano you may be able to fine tune the piano yourself. It might come with certain presets, right? To say, I want it to sound like a concert piano versus an upright versus, an organ. And then the really fancy digital pianos, you can even upload your own waveforms, your own description of, like, I want to tweak it a little bit. It should sound a little like this particular style of upright piano or baby grand. And you can tweak that. And I'm handing it to Kevin here, right? That's kind of like fine tuning. I'm going to try to work with Joel's piano analogy here. And I apologize to musicians here.
Keep it going.
I like to get my analogies and my metaphors in first, so that Ken gets
so
stuck
we have to use them. Yes, now because it was trained in and it's baked in, and now we all have to work with it.
Yeah, so fine tuning, and I'm not going to even attempt to talk about pianos, but Fine tuning for us historically has been when the context windows were a lot smaller. Now they're expanding. And what was happening was we were trying to pass too much information to the model at inference time. And we've backed away pretty heavily from fine tuning. There are cases in which we use it, and there are people that do like to use it. But the idea behind fine tuning is, as Ken said, is you do freeze the weights. So now you're going to have reproducible not deterministic. In LLMs, you never get that, but you get something that is frozen to behave in a way in which you want it. We usually like to use it for very small tweaks. Massive behavior changes, you're probably using the wrong model or tools when you're leading into it.
So during inference, do the weights ever change based on what I'm telling it or how I'm shaping it?
The weights are frozen during inference time. The context will, I like to think of it as I'm performing, it influences it, but I'm actually performing inference on more data.
Yeah.
If I was to try to take a system and I wanted to pass in a fruit and have it classify it as a fruit or a car and have it classify it as a car, if I say apple to an LLM, it's going to say something crazy. If I was to give it a few shots, what we call few shot inference, which a few examples of like apple equals fruit, banana equals fruit, like Hyundai equals car, the system will learn those rules, but you're performing inference on that whole thing. So what you're performing inference on is actually different. People think of that as learning. It is clever because activation layers allow you to look back at prior data to influence your future results.
Right.
Hopefully that makes sense.
Right. It's sort of like maybe I'm talking to a 5-year-old and they know something about the world, but they don't know what's called a fruit versus, say, I'm going to pick something, an animal, right? Go, well, that's a fruit. You point at the banana and an apple and so on. And then you say, well, these are animals. You point to the dog and the cat. And you go, these are animals and these are different. They'll generalize off of that. But unlike an LLM is a little bit unlike a human in the sense that a human will get that from the example and then over time they'll bake it into their model. We don't quite have that yet, but people are working on it.
Mm-hmm.
But it's sort of like what's hard-coded, what's baked in, the fixed weights.
Yeah.
What's in the piano you get from Yamaha versus what are you tweaking by where you're placing the piano and maybe what instruments you're placing next to it.
I feel like we're approaching training is an apple, but then we get an orange and that's inference. And so it's different. It's, but so what, you're talking lots of memory. You need it in both. You need GPUs for both. Obviously, when you're training, you have different, and I hear this word a lot, pipelines that you don't have with inference, right? So what do you need in those pipelines? You have lots of data, you have lots of information, you have different security needs. So what makes up a pipeline, Kevin? You've built them. So what goes into a pipeline? Well, I hear you built them.
Well, right? Yeah. I mean, for us, it's tons of compute GPUs and tons of data. Now the security needs of us is we like to think of security as that if I didn't train something into a model, I don't have to worry about it saying it later, right? So when these LLMs are trained, they're trained on massive amounts of data, and you ask it questions and it answers inappropriate things. If we like to make our system so that it's never been trained on that stuff. So we have to worry about it coming to us.
So the choice of ingesting Reddit was basically the first problem. Like way back, that's where it all started. That makes sense, right? Controlling the data coming in is actually a security issue. Like, don't put top secret stuff in there because it'll spit it out later. I mean, it should be obvious, but maybe it's not. So controlling the data is actually a technique. And then on the reverse, it's also controlling the response, which is data coming out. So you're kind of doing the same things, but in reverse, isn't it?
Yep.
Yeah.
There you go.
Kevin's
you hit it right. You hit the nail on the head. This is one of the key differences between inferencing and training. Training, you're baking it in. It's in the piano. It's in the model, and it might be hidden. It may be hard to pull out, but it's in there somewhere. Whereas with inferencing, you're saying that's not in there. If I have some proprietary data that I don't want to share and I don't want to be baked in the model, but it's still useful to you, then I'll do the few shot learning, the expanded context window that Kevin talked about to give it that information. So that's an important reason why you might pick one over the other. I need my model to be good at, I don't know, spotting Russian nuclear silo sites, but I don't want it to be put in the model. So instead, what I'm going to do is I'm going to take a model off the shelf and I'm going to then give it examples of this is what a silo site looks like, and let it and say, okay, now that you give me some examples, I can find others.
Yeah. Right. And it can be very powerful by attaching it to a knowledge base. And now you can change that knowledge base. You can remove things from it. You can add things to it. The other thing it allows us to deal with, different tenants in the system. So if I want information specifically for Joel about pianos and then Ken about fruit, I can have the knowledge base contain relevant information. And that allows us to keep, stuff that should be secret out of individual deployments.
Right.
Right. Well, and I think part of the reason that people started believing, or at least have gotten the idea that during inference they can learn, is because of the systems around it. When you look at something like ChatGPT, there's also a lot of session data. It saves your conversations. That's not the model. The model's not doing that. That's the systems outside of it, the server and the, everything that goes along with it. And it's starting to sound like it knows you more because it's building more of that context and sharing it every time. So it knows, hey, this is who this is. This is who've been talking. These are the key points, right? Remember these 5 things, right? Yeah. Lori likes this. She has fish. She doesn't like dogs. It should remember this, but it doesn't, right? If the entire system went away, the model would forget everything. And I'd have to start over rebuilding that context, right?
Yeah. Now, there is a difference we've been talking about pipeline, and I think that's a good discussion. And what we're talking about is an ingestion pipeline for the data set. Now, once you get inside the ingestion, you also have a distribution pipeline to take this work and split it apart and do your normalization passes and feed it in to GPU processing, et cetera. And that is also where some differences between training hardware and inferencing type hardware exist as well. The memory needs are much higher on the training side, but also, most importantly, the amount of memory bandwidth that you have to feed things into memory and clear things from memory, the faster the memory is, the better. On the inferencing side, you can take a little bit of delay. It's always best if you can get the fastest memory possible, but it's actually less critical. And so if you're looking to save money, you can use lower speed memories with inferencing, but that's really the only difference in the two pipelines. Yeah. So like on the training side, HBM memories are a great place to keep this training data because you're doing a lot of operations, and it's about loading and unloading and doing these atomic operations. On the inferencing side, you're basically loading once and you've got an intermediate set and you discard it after you're done. And so the memory is different inside the processing pipeline.
Yeah. And speaking as a former hardware person, it's really about that memory working set, as Joel said, right? For inferencing, the memory you need is whatever it takes to hold the model, usually measured in double-digit gigabytes. Not trivial amounts of memory, but not huge amounts of memory either, right? You need 10, maybe 100 gigabytes of memory to hold your model. And once you got that, getting more memory is not really all that useful. Compare that to the amount of data that you're training on, which is, petabytes of data. And so you're never going to keep that right next to your silicon, next to your GPU. So that memory bandwidth, getting those petabytes of everything on Reddit in and out, that's your bottleneck.
Yeah. So from a design perspective, you definitely have to take all of those things into account. And it's in multiple places. So you've got the ingestion pipeline, you've got the processing pipeline, you've got optimization functions, the whole 9 yards. You have to look at each step of the pipeline and choose exactly the right components that give you the most efficient and cost-effective way of processing. And that's where the major difference is in inference between inferencing and learning. Although the training and inferencing have the same mathematics behind them, the actual hardware is different. I realize I've come around in a full loop there.
You have. I mean, that's okay, because you were so close to like the perfect like takeaway. It was right there, right? Like
Yes.
It's different compute. You have to identify the steps and put the right things, and then you right back to the math is the same. Though, well, of course, like 1 + 1 is 2, no matter whether I do it, a 5-year-old does it, we do it on an abacus, we count it using M&Ms, or the computer does it. The math is the same. That should be evident, Joel. Yes. It's irrelevant.
Yes, but let me talk about pianos for a half hour, so I'm good.
Well, that's true. That's true. I think that is our takeaway. We are way over time, right? Is identify the stage that you're working at. Look at what you need for each in terms of components, and put the right things in place to optimize each of these phases, because they're both important. Right? And you don't train something to not use it then in inference, and if you can't inference if you haven't trained. So they kind of go together like peanut butter and jelly, or pianos and Joel. So,
exactly.
That's right. Well, thank you all. That's a wrap for Pop Goes the Stack. Please subscribe, so when the good stuffs arrive, you'll recognize it even without a keynote.